Hi everyone. So in this video, it's just a recap of what we have done so far in terms of discussing aspects of a design of a deep neural network, and an open discussion of the other aspects that we'll discuss going forward. So remember, at deep neural network, you have the input layer and then a bunch of layers. These layers have hidden layer activations and then the output layer. And then after the output layer, you apply the cost, right? And then you use gradient-based learning to optimize that cost. So if you think of the design consideration factors, let's say you have a new problem and you want to design a network, right? So what are the aspects that you have? One of the aspects is the number of layers, right? So the depth of the network, right? And then, so this, we will have a thorough discussion of that factor later on. But not only the depth is important, but the connectivity pattern between the layers is also a very important factor, right? So for example, you could have a fully connected layer where every neuron in the layer before is connected to every neuron in the layer after, right? So just to avoid confusion, we will use the term layer interchangeably. Sometimes we will use it to mean the set of neurons, and sometimes we will use it to mean the connections between two sets of neurons, right? Just to be precise. So a fully connected layer is a fully connected bipartite graph between a set of neurons and the next set of neurons. Later in the fourth section of this course, we'll discuss convolutional layers, right, which are much more sparse than fully connected layers. So in a convolutional layer, a neuron in the first set is connected only to few neurons in the second set, and these neurons happen to be neighboring to that neuron, right? So it's more of a locally connected bipartite graph. And one of the important questions to discuss when discussing what type of layer do you need, of course, there is a question of whether it's feedforward or recurrent, and that we'll discuss later in the fifth section of that course. But another important question is whether the layer should be sparse or dense, whether you should have a lot of connections or few connections. And there is very little understood about that in terms of neural network, but there is a lot that's understood in graph theory. So we know a lot about properties of different, so you can think of these layers as bipartite graphs, right? So a bipartite graph is a graph where only vertices in one set can only be connected to vertices in the other set, right? So there is a lot that is understood about properties of different bipartite graphs, but unfortunately that knowledge hasn't transferred yet into understanding the impact on learning of the different connectivity. But we can use some of the insights or some of the known things about the properties of graphs to sometimes say the intuition behind different layer designs. Now, remember we said depth is only useful if you have nonlinear activations, and then we had the only exception is linear activation. And that's really an exception in terms of reducing the number of parameters, but you could always remove the linear activation layer and learn whatever you were learning before you inserted that layer, but with more parameters, so with more cost. So depth is only useful if you have nonlinear activation. So the choice of nonlinear activations actually is a big decision in learning, and we discussed so far rectified linear units that are typically used in feedforward networks, and hyperbolic tangent, or the variant of sigmoid, as a nonlinear activation that's typically used in recurrent neural networks. We also discussed choices for the output layer, whether you have two-class classification problems, you have the softmax output layer, or multi-class classification problems, you have the softmax, sigmoid, for two-class, and softmax for multi-class. In general, even if it's not a classification problem, what sigmoid is doing is that it's approximating the maximum likelihood principle for a Bernoulli distribution, and softmax is approximating the maximum likelihood principle for a multi-Nully distribution. We also discussed the cross-entropy cost function, and we said we are restricting our attention to classification for this course, and most of the arguments will transfer easily to regression problems where the typical cost function is the mean square error or the MSE error, which is basically the L2 norm or the squared distance between the value in the real line. It's the squared distance between the value you are estimating and the true value. And the L2 norm is an extension or the Euclidean distance in Rn. In general, if you have multiple dimensions, each dimension is a real number. Now, we said we didn't discuss how the gradient will be computed, right? So we said we are mainly focused on gradient-based learning. This is what the deep learning approach depends on mainly. So a major part or a core of implementing deep neural network algorithms is basically the algorithm of how to compute the gradient efficiently. And for that, starting from the video after next, or two videos ahead, we will start discussing backpropagations. Backpropagation algorithm, which is basically an efficient way to compute the gradient using a property of that gradient to decompose it into modular computations, and these computations can be used for multiple steps, right? So we'll discuss that in more detail later. Another thing we will discuss so you compute the gradient, and then after you compute the gradient, you want to minimize the cost. Use the gradient to minimize the cost. So there, a huge component is the optimization strategy, and we'll discuss that in the third section of that course. I will discuss multiple algorithms, starting from stochastic gradient descent or SGD to root mean square propagation with RMS prob to ADAM or the adaptive momentum algorithm. And ADAM is the one that you see a lot in the deep learning implementations using TensorFlow or PyTorch. We'll discuss the justification behind these algorithms. Now, in the next video, we will focus on the depth question, right? Because that's a very important question, which goes back to the first point, the number of layers. And that question should not, any of these questions in general, number of layers, connectivity pattern, nonlinear activation, output layer, cost function, backpropagation, or optimization strategy, all of these are interconnected, right? As you will see throughout. So you cannot answer one of them independently, but we will discuss the important points to consider or the important design considerations that makes you determine whether you need more depth or less depth. So say you have a problem and you bring a 2-layer network and then you do a little bit of testing. You want to know whether this network should be a 1-layer network or a 3-layer network, right? So which direction should you go through? Thank you.